We've all seen one of these. This is a periodic table. Now, everybody has their own different comfort levels with periodic tables. When I explain them, one of the analogies I like to use is when I compare it to the alphabet. We have 26 letters in the English language, and depending on how you combine these noises, these letters, you can make up for just thousands and thousands of words in the English language. Well, the same can be said. Similar thing happens when it comes to this periodic table. Every single one of these elements makes up all of the matter, all the stuff that you see in the universe. Your table, your skin, animals, the air that you breathe. It's some combination of all of these in order to form some type of matter. Understanding them is all about understanding patterns and understanding its properties. So, another analogy. When you come across these little puzzles on Facebook that are so fun to do, you start off with little pieces of information. You don't even necessarily start with the beginning of the equation. You might look at one of these down here and be like, oh, okay, I have to solve this in the end. So these three candies, they look the same and they equal 27. You multiply them together. Oh, okay, well, the only number that that repeats itself, like it has to be the same number and you do it times, is gonna be 3. So I take that and then I apply it here to figure out what this is gonna equal. Yeah, all that kind of stuff right here where you find out a little bit of information. You take a little bit of information, you crack the code for one piece of information, and then you're able to solve other equations. You're able to solve other problems. You're able to find out more information. This is what Dmitri Mendeleev did when it came to the periodic table. Back in his time in the 1800s, he, scientists had only discovered a handful of these elements on Earth. However, he started to begin noticing a pattern when it came to the properties of the elements. So, you take something like cobalt over here. A lot of it's found, most of it's found, I think, in Africa. It hadn't been discovered yet, for example, but what he did know is that it had an atomic number of 27. And based off of what other elements that had similar characteristics in its family, he was able to describe what cobalt might look like. Didn't know the name of it, didn't know what it looked like, hadn't been discovered yet, but based off of information that he had with other elements, he was able to fill in the gaps of this and eventually create a table. Not knowing what the names of these elements were, but rather what their properties were going to be. So, one of the easiest ways to start to understand the periodic table is to look at an element and know what these little numbers mean. I'm gonna avoid these, the ones with the decimals for now. Not a big deal. It's called the atomic mass. I'll get to why we have that. The most important thing I want you guys to know is the number on top of the element. The number on top of the element is called, get ready to draw. The number on top is called the, that's not a good A, atomic number. Atomic number, fancy word for the number of protons. So this is extremely important. The atomic number, which is only, the number of protons for an element, that's important to know because the atomic number is going to tell you, it's going to give you the identity of the element. Now, what do I mean by that? Well, what I mean is this. Hydrogen, based off of what I said, has an atomic number of 1, which means that it has 1 proton. The atomic number is the number of protons. So hydrogen always has 1 proton. If it's, you see something with an atomic number of 2, it's not hydrogen. It's going to be something else. If you see like lithium here on the bottom, the atomic number is 3. That means it has 3 protons. Lithium always has 3 protons. If it doesn't have 3 protons, then it ain't lithium. As you increase, you will see, as you increase the atomic number, you're going to have a completely different element. But just know that something with 4 protons, it's always going to be this particular element, beryllium. Something with 11 protons is always going to be sodium, nothing else. It's sodium. So the atomic number, which is the number of protons, is always going to give you the identity of the element. Now, when it comes to what these, pretend like you have super eyeballs and you can see atoms. Like you could, your microscopic viewing, you could zoom in on things and see things at the smallest form, which would be awesome. Atoms in reality, they look closer to this. I'm sure you guys have seen stuff like this on TV. You see like, ooh, science, ooh. I can't really draw it that well, actually. Okay, this looks like a mess, but I'm sure you guys have seen these little atomic molecule things in shows or movies or whatever. It's more, that's a bad example, but that's more realistic than what I'm about to show you, which is how we look at elements and how to draw to see what they look like. So we use something called the Bohr model. Because this is boring. No, I'm just kidding. It's because there was a guy named, his last name was Bohr, so he named it after himself. So this Bohr model is very simple. It takes the nucleus, the middle of an atom. So any one of these elements that are on here. The nucleus, let me make sure I spell this correctly. Nucleus is going to have the protons and neutrons. I'll get to what all those things mean. On the outside, circling around, are the electrons. Electrons move. Go, they're circling around the nucleus. So this is what an element would look like. Now, elements typically have protons, neutrons, and electrons. They have charges. I want you to think of magnets because magnetism does come into play when it comes to chemistry. So protons have a positive charge. We use a little plus to express that. Electrons have the opposite. They have a negative charge. And neutrons, you hear people say has no charge, but the best way chemists, they say that it has a neutral charge. And they use like a little zero with a slash going through it. So this is all the information you need to construct any one of these atoms, see on a basic level what they look like. We can start to begin to visualize and look at their patterns and at their properties. Okay, so let me go ahead and clear this out and let's start doing some Bohr models. So let's take hydrogen. So hydrogen, as we said before, has an atomic number of 1. That means it has 1 proton. Our protons and neutrons go in the middle, right? That's our nucleus. Well, in this case, I'm going to put a little p right here because it only has 1 proton in its nucleus. Okay, this is the nucleus, the middle. Around it we have our first energy shell. Okay. Now what's cool about this, you see over here where it says period, it's kind of cut off, but it says period. Everything going horizontally from here, and then we'll get to some other elements that are on this side, they all have one energy shell. That's what the periods tell you, how many energy shells it has. So hydrogen has one energy shell, and on that one energy shell, it has one electron. Okay, so we're going to keep everything balanced. We're going to have one proton, one electron, and what the heck? Why not? One neutron in the middle. So remember, the protons and the neutrons are your nucleus, and then you have your one electron circling around on its energy shell. Okay, negative charge, positive charge, positive charge, and then your neutral charge. If I were to, list this out, I got my one proton, which is positive, and I got my one electron, which is makes it better, plus, which is negative. And I got my one neutron, which is neutral. So I'm not netting anything. This is perfectly balanced. Not all elements are like this, but we'll get to that later. For now, in a perfectly balanced world, it's not more positive, it's not more negative, it's nice and balanced. There's no charge to this element. Okay? And by the way, we put like a little dot. This is the one electron that's going around. Okay? Maybe I should have drew it closer to the E, but whatever. So you got your one proton, your one neutron, and then your one electron. Let's do another one. Let's do lithium. Now notice my period is changing. Oh, it's in the 2 column. That means everything, even all the way up to boron and the other parts of the periodic table. I can't zoom out right now because I'm doing the whiteboard, but everything horizontally going across has 2 rings, 2 energy levels. But let's start off with the nucleus. So for lithium, as a reminder, I'll put lithium. We have an atomic number of 3, therefore we have 3 protons. I'm gonna put 3 protons. And you know what? They're gonna be stuck together like M&Ms and Skittles. I'm gonna put 3 neutrons in there. Typically, that's what it looks like. They're all bundled up and tightly packed together. So they're stuck together in that little nucleus, okay? Nice little family. Now, electrons. Right now, we have a net charge of 3 positives. We have 3 positives and 3 neutrals. So this is positive right now. We're gonna balance this out. I don't want it to have a charge. I don't want it to be positive. I want it to just be okay. So again, here's one energy level. And I'm gonna have, this is important to remember, you can only have 2 on the first energy level, no more than that. You only get 2, okay? So 2 electrons, 1, 2. But I still have more positive than I do negative. I have 3 positives, 2 negatives, and then the neutrons are neutral. So this is more positive right now. I'm gonna have to add, and that makes sense because remember the period, did not mean to do that. The period tells me that I need to add a second energy level because I can only hold 2 on the first one. After this, every single ring can hold up to 8, but for that first one, it's only 2 electrons. But I don't need 8 electrons. I only need 1 more because the atomic number is 3, and the atomic number tells you the number of protons. And in this, for the examples that we're doing right now, we're gonna match the number of protons with the number of electrons. Therefore, 3 protons, 3 electrons. 1, 2, 3. And I am gonna label these just so you guys remember. This is electrons, and they all have negative charges. Okay? So right now, for the electrons that have a negative charge, we have 3 of them. For the protons that are positive, we have 3 of them. And then for the neutrons that are neutral, we have 3 of them. This is a perfectly balanced lithium atom, lithium element right there. I'm going to do one more example so we get the hang of this. Next up, sodium. Why it starts with an N and an A, I have no idea. Notice how the period level, the period's changing. Remember, this tells us how many rings it's going to have. And now it's saying 3. Let's see. Now at this point, I am not, the atomic number is 11. The atomic number, there we go. Atomic number is 3, oh, just kidding, is 11, whoops, is 11, which means it has 11 protons. After a while, these numbers get so big, I'm not gonna sit here and put like 11 P's in one place. So I want you guys to just know at this point, I'm gonna put the name of the element, which is Na, sodium, 11 protons in here. And for now, 11 neutrons. This is my nucleus. Now, how many rings am I gonna need? 3. 1, 2, 3. Why am I gonna need 3? Well, let's do this. Actually, I'm gonna use a different color too. Let me get some blue in here. Now, who remembers? The first energy level can only hold 2. So 1, 2. Okay, great. I want to match my protons and electrons. So right now I have 2 electrons, but you know what? I want to have 11 to match the number of protons. So I need 9 more. Well, I can only hold 2 on the first energy shell. For every single energy shell after that, I can hold up to 8. So on this next one, I can hold 8. So let's see, I got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, I gotta stop. I don't have any more room. I can only have 8 at the most after the first energy shell. So right now, I have a total of 10. All I need is 1 more, and I can add it on this outer shell. So now I have a total of 11 electrons. So far, what we have done is taken an element and we've used the Bohr model to show the number of protons, which will always go in the middle, the number of electrons, and how many rings, how many energy shells the electrons are going to go on. In my next video, we're going to go more into why this is important to know these things, and what the atomic mass is, which is these numbers with the decimals. Seems confusing, but it's not. Anyway, hope this was helpful. Peace.